Hello, today we're here with Daniel Povey, and he's going to take us through some issues with text search. So, can you tell us what this repository is and what are the special features of K2FSA text search?
Okay, so K2FSA is a GitHub organization for our so-called next-gen CalD. It was originally the organization for our K2 project, but it's grown to be where we put most of our next-gen CalD stuff. So now this text search project, it's a project that we split off, and it's for handling a special kind of problem where you have recordings and you have text, and you need to align them so that you can split them up into chunks for training speech recognition systems. So the idea is you might have an hour-long call or an hour-long TV program or half an hour recording of something, and you have a long text that goes with it, and you want to get small chunks with aligned text and audio. So now the core of it is a kind of a cool technical idea. So now the basic setup is we assume that we already have a recognizer that somewhat works in the language concerned. So let's say for English. Now let's go to example slash LibriHeavy. Okay, let's look at run.sh. Okay, scroll down a bit. Okay, wait there a little bit. So now that JIT script.pt, we will have downloaded that from somewhere. I'm surprised that that isn't mentioned in the that JIT script.pt will be some kind of, it'll basically be a model that we've trained earlier, probably a zip form or
Where's
something
JIT
like
script?
that. Go down a little bit. It's it recognize.py. It's one of the args to that. Yeah. And then model file name, it's that. So that's probably some kind of English zip former model that we've downloaded. It has a very generic file name. I expect some part of the script above must have downloaded that. But so when we train a model, it gives us a checkpoint file, a .pt file containing like all the model parameters and some other stuff. And then there's a special script like export.py, I think, that will do something called torch scripting or tracing, one of those two, and creates another .pt file that's like, but basically it allows you to run the recognition without depending on torch, I believe.
It's
No,
PyTorch, not PyTorch dependent.
I believe it's not PyTorch dependent. It might depend on only something like Onyx. Can we let's have a look at tools/recognize.py.
And also, I think when I ran this,
Yeah.
you have to we downloaded like some icefall recipe,
Yeah.
and then we just renamed it to exp and everything worked. The JIT script is in.
Okay, fine. But I'm still, so what I'm confused about right now is I don't see in tools on the left there, I don't see a file called recognize.py. So I'm a bit confused where that came from, whether we like downloaded that from somewhere else.
Um, let's see. Tools. Recognize.py.
Maybe it's a different tool. Okay, click on that. Oh, you found it? Oh, cool.
Yeah, you
Okay.
can also download the JIT model.
Oh, okay, cool. Okay, so it looks like it is importing torch. I'm wondering how much it really depends on touch. Well, I don't see anything about Onyx. So normally when you make it so it doesn't depend on touch, you output in some kind of Onyx format, which is like a generic neural net format that's supposed to be platform independent. And then there's ways that you can run that, but this one doesn't seem to be doing that. But I think it has got rid of certain other dependencies, like on K2. So maybe we're just depending on touch now. That's not too bad. Okay, so basically this does a recognition and it'll output the text in some format, but the text will be all uppercase. It won't have mixed case and punctuation because this ASR system was trained on LibreSpeech that was all uppercase. Now, what we actually want to do here is we want to eventually align the text and get the mixed case and punctuated reference. So one of the things we do is before we do the alignment, we uppercase the reference and we remove all the punctuation. But then we remember the source for each position. So when you remove punctuation, it will shorten the string, but we basically remember for each position in the shortened text where it came from. So there's some kind of mapping that it keeps internally. Now, the next thing is we have to align the recognized. So the recognized text from this recognized.py script, it's going to come with timestamps. The script works out the time corresponding to each token of text. Now the tokens, they're BPE tokens, they're short sequences of characters. But we can just treat it as if there's a time for each character. Okay, so we have the times for each character, and we need to align the recognized text to the reference. So the basic way that you would do the alignment is something called Levenshtein alignment. It's the same thing that you use when calculating word error rate. Unfortunately, that is a quadratic time algorithm. So if there's, let's say, 100,000 characters in your article or whatever, it would take approximately 100,000 squared like operations to align it. Pardon me. And unfortunately, for the sizes of data that we're normally trying to align, it's just too long. It takes like longer to align it than it did to recognize it, which is ridiculous. So we have a kind of neat solution to that. It uses this rather fancy thing called suffix arrays. These are a kind of a special data structure that was developed for use in DNA processing. And it's basically you take a long sequence of characters, say, and you sort them in lexicographical order by the suffix, kind of reverse lexicographical order. So the last character gets sorted first by the suffix ending at each position. Anyway, so what we do is we do that suffix array thing on the concatenated like reference and transcript. And there's some fancy algorithm where basically we figure out what the alignment is in O of n log n time. The way that you can think of it is, imagine you have a matrix of like 100,000 by 100,000, and there's little dots wherever there's a close match. Basically, wherever two suffixes are like the closest to each other in the reference versus the text. Now, it's going to be random looking, but there's going to be a diagonal-ish line where it's kind of enriched in those little dots, because that's where the actual true reference is. So the idea is to discover where that diagonal line is on the scatter plot. And the way that we can formulate that is to find well to find the sequence of dots that you can, that's the longest possible, that you can go like upwards and to the right, but you can never go to the left or downwards. So always upwards and to the right, get the longest possible sequence. And basically, we found an algorithm that you can do that in O of n log n time. And it relies on the C++'s map class, or maybe it's the set class. I think it might be the set class. Well, it's map or set. And those classes have a complicated implementation, but it relies on the fact that you can kind of look things up in O of n log n time. I forget the details of the algorithm now, but it's not very complicated if you look at it as just operations on map and set. Now the internal implementation of C++ is map and set are very complicated, and it involves red-black trees, and I don't know the details at all. But anyway, it works, and that's good enough for me.
Have
So
that.
yeah, you go on.
Do you have that table somewhere in this project?
Wait, which table? Oh,
Like you said, you mapped everything and it was going diagonal.
yeah. Well, okay. So we never physically construct that as like as a big array, because the array would be too big. It would take quadratic time to construct it. But what we do is basically we have it as a sequence of points. So each point in that array, you can represent it by a pair of I and j, where I is the index here and j is the index here. So basically the way the algorithm works is you sort the I and j indexes on I and then j. I think that's, or maybe it's I plus j, I forget. You sort them in a particular way and then you process them sequentially. And I forget the details of it, but it's an operation on that list of points, and the number of points is basically, I think it's 4 times 100,000 in the case where I and j are length 100,000. So it's manageable. It's linear basically in the input size.
So do you have to, in the code, you have to reference that table a lot? Like, do you have
So
those coordinates in this repository? How are you?
they are referred to in this repository. Now it'll be in the actual text search Python the Python package, not in the examples. So click on the text search directory. That might be the actual Python package. Yeah, okay. Yeah, let's go to Python.
I did go to Python.
Oh, okay. Click on text search. That's probably the actual
Suffix?
Wait a minute. No, that's probably some wrappers for C++ because the suffix array had to be in C++. Let's click on match.py. Okay, I keep going down. Yeah, okay, so you see those I's and J's. This is, I think this get longest increasing pairs is the thing that I was just talking about, where it finds the path through there. And basically all of the non-trivial code is in C++ for speed. So those things that have an underscore at the start, like get longest increasing pairs. Oh, well, those are, okay, those are internal implementations. So sorry, those are not C++. But let's go down, see if we can, or maybe it's up. Maybe it's at the top that we imported that from some C++ package. Oh yeah, from underscore text search import underscore, we're importing it as underscore get longest increasing pairs. So now C++ code can easily operate on NumPy arrays because NumPy arrays are just backed by basically like a C array of integers. So there's ways that you can access that from C++ code efficiently. So anyway, that's where it's happening. It would be probably inside. If you go to the C source directory that's not inside the Python, that would be where the actual algorithms are. I don't know that we really want to look at that.
Okay.
Yeah. As you can see, it's not me who actually wrote it. It's Canway from my group, so I don't recall all of the details.
Okay. What was my next question? Oh, okay, let's go back to in run.sh, you okay, in run.sh, you mentioned a lot in master 1, 2, 3, 4, 5. What is that?
Oh, that's just a port address. So for parallelization, so some of the ways that you parallelize thing in Python requires you to have a port address for the processes to connect or something. I think this isn't even really necessary if you are on a local machine. I think maybe it's because the parallelization process is something that in principle could work on multiple machines, and they somehow coordinate via a port number. And basically, if you have two different processes running on the same machine of that, you have to give them different port numbers, or it won't work. The second one will die.
Oh, okay.
It's SSH is port 22, things like that. But like for the very large port numbers are usually reserved for just random stuff you want to do.
Okay. I think I had one more question from
Oh,
this.
by the way, this example, the Libri Heavy, what we're doing is Facebook released a Libri Lite data set where they list the audio of a bunch of audiobooks, but they don't give you any reference. So we're basically aligning that to the reference. That's what Libri Heavy is. We haven't released it yet. It's kind of a work in progress.
Okay. Oh, actually, my question for this was in their data set, the audios, a bunch of them match to the same text. Like 5 audios would match to the same text. Why are so many?
Oh, I think what that is it has different chapters or something, or different sections of the book. So I assume those different audios are actually mapping to different parts of the text.
Oh.
At least that's I believe. Yeah.
Okay.
Yeah.
In run.sh, you have max duration, but when we did max duration 2400, it said there wasn't enough space on our GPU to handle that. So we decreased it to 240 and it worked. Can you explain what decreasing it would do?
Okay, so the max duration is the total number of seconds in the batch because it's recognizing in batches. On GPUs, it's important to batch everything up because that's how GPUs are fast, by batching stuff. So the GPUs that we ran this on have 32 gigabytes of memory, and most likely yours have less. So let's suppose you have 16 gigabytes, you should probably set that to 1200 or a bit less because the model itself adds a certain fixed amount. So probably 1000 would have worked for you.
Okay, and this wouldn't affect the quality of the output, it would just be slower?
Yeah.
Okay, thank you.
Bye-bye.